السلام عليكم ورحمة الله يعطيكم العافية. راح نكمل اليوم ب chapter 12. وصلنا عند general energy equation. أتمنى الكل يكون بخير شباب وصبايا. المرة الماضية خلصنا البرنولي equation and its applications besides efficiencies ل mechanical و electrical devices. هلا راح نبلش بالجنرال انرجي ايكويشن. تذكير بالجنرال انرجي ايكويشن اللي مرت علينا بشابتر 3 وبالثيرموداينامكس بارت as well. This is the energy equation in its energy form, or this is the energy equation in its rate of energy form. Here a reminder of the specific energy, specific mechanical energy, where it's the sum of the internal energy, kinetic energy, and potential energies, which are in their specific form, are as shown here. The net input heat rate is given as the difference between the input and the output. Similarly, the net input power is the difference between the in and out. So the energy analysis of steady flows, if we look at the equation that we used back in the thermodynamics part, chapter 6, it was as shown in this equation. The net shaft input power is shown here. This is the net input heat rate, while this is the energy transfer between the in and the out. That's for steady flows, where the dE, d time term, this term is 0 now. So if we have a single stream, then the summation notation will be dropped, and we will have simply the equation as shown in this form, and that for the single stream flows and devices. In its specific energy form, simply divide this equation by the mass flow rate. It results in the specific energy form, and which may be rearranged according to this equation. We put back the enthalpy in its original form as the sum of the internal energy and the flow energy. So put the change in internal energy together with the net input specific heat as this in the right-hand side of the equation. When we have the net input heat equals to the change in the internal energy, that's considered as an ideal flow. There are no mechanical energy losses. In case not, then this represents the mechanical energy losses in the flow, which is actually, this is the case for the real flow. The mechanical energy equals to the mechanical energy output plus the mechanical energy losses. So put these mechanical energy losses back into the previous equation, and knowing that the net shaft input work is a result of as the work for power consuming devices or work consuming devices such as pumps, fans, compressors, minus the work the delivering or producing work devices such as the turbines. So I'll put these back into the previous equation, and the equation becomes in this form. Okay. Now, if we multiply this equation by the mass flow rate, we then retain the power form of the energy equation for steady flow. And here the E dot, the mechanical energy power, the mechanical power losses is given in this equation. The mechanical power losses represents the mechanical power losses in the pump, plus the mechanical power losses in the turbine, plus the mechanical power losses in the piping. Okay, while this here represents the pump power, this represents the turbine power. Okay, the energy equation in terms of the heads, then we may get this by simply divide this form of the equation by the gravity acceleration, then we will have the energy equation in terms of heads, and it becomes in the head form as shown here. Now, as we can see, the head form for the pump is called the useful pump head. The head form or the head term for the turbine is called the extracted turbine head, while the head term for the mechanical energy losses is called the head losses or the losses head. The head loss or the loss head. So the useful pump head, the different relations between the specific useful pump work, the useful pump power, and the efficiencies that we introduced back in chapter 3 are shown in this relation here. Similarly, for the extracted turbine head is its relation with the specific turbine, extracted turbine work, the extracted turbine power, and the turbine shaft power are also shown here. So the pump power shown here, this represents the shaft input power to the pump, while the turbine power term here is representing representing the shaft output power from the turbine. Okay, while the head loss here and its relation with the specific piping mechanical losses, okay, specific piping mechanical losses energy and the piping mechanical losses power shown here. Here, this schematic showing what happens to the flow. As we can see, the useful pump power adding to the flow energy. The mechanical losses in the pumps are taken out here from the pumping power input, which is the shaft input power for the pump. While for the turbine, the extracted turbine, this is the turbine power, the output. The extracted turbine part of it will be taking as the mechanical losses in the turbine, and the rest is going out as the turbine shaft output power. Okay, here's the mechanical losses in the piping that is included in the energy equation shown in the previous slide. So the equation, the energy equation for a steady flow in its head form is shown again here in this equation. Okay. Now, as a comparison between the energy equation and the Bernoulli equation, if we look here, if we don't have shaft work devices, that means this term and this term will disappear. And case we don't have losses in the flow, then the equation, the energy equation reduces to the Bernoulli equation. Okay. Introducing the kinetic energy correction factor. Actually, this equation and all the previous equation where the velocity term appear, we were assuming that this is the actual velocity. The actual velocity in terms of the mean velocity, that we usually find and calculate. So this average velocity need to be converted to the actual velocity by multiplying by the kinetic energy correction factor. So here, this is the uh, velocity head, so it needs to be multiplied by the kinetic energy correction factor. The kinetic energy correction factor equals to the actual kinetic energy power divided by the average kinetic energy power, and it has this integral form. So once we know the velocity profile as a function of radial coordinate, we may be able to calculate the kinetic energy correction factor, In general, the kinetic energy correction factor equals to 2 for fully developed laminar pipe flow, and it ranges between 1.04 and 1.11 for fully developed turbulent flow in a round pipe. So after introducing the kinetic energy correction factor, this is the final form of the energy equation, whether in the power form or in the head form. So if there is no information was provided for the kinetic energy correction factor, we simply assume that it equals to 1. Okay, now we'll come to a couple of examples. So if we go back to the examples from our textbook. So now let's look at the examples. Okay, so here the energy analysis of steady flows. We showed all these equations, terms, and finally talk about the kinetic energy correction factor. And here, let's look at these examples. Here in example 12.5, it tells us that the pump of a water distribution system is powered by a 15 kilowatts electric motor. 15 kilowatts electric motor, that means this is the input electrical power to this motor is 15 kilowatts, whose efficiency is 90%. The water flow rate through the pump is 50 liters per second. The diameters of the inlet and outlet pipes, are the same here from the pump. The elevation difference across the pump is negligible, so that means Z2 minus Z1 is negligible. If the absolute pressures at the inlet and outlet of the pump are measured to be 100 kilopascal and 300 kilopascal, as expected, the pressure will increase at the outlet of the pump. Determine the mechanical efficiency of the pump, and the temperature rise of the water as it flows through the pump due to the mechanical inefficiencies. This temperature rise, the mechanical efficiencies means the mechanical losses due to the mechanical losses in the pump. So first, what do we need to do? In order to find the mechanical efficiency of the pump, we need to find the shaft input power to the pump, which we refer to as the W dot pump. And then we need also to find the useful pump power. Which represents, as we discussed back in chapter 3, it represents the mechanical power increase of the fluid across the pump. So here, from the efficiency of the motor and the electrical input power, we may find the shaft output power from the motor, which will also be equal to the shaft input power to the pump. This is the first step. So the shaft pump power equals to the efficiency of the motor times the electrical power of the motor. So that becomes 13.5 kilowatts. So now we know the pump shaft power, Also, now we have the volume flow rate of the flow. Since it's the same diameter, the mass flow rate will simply be the density times the volume flow rate, which here that equals to 50 kilogram per second. 50 kilogram per second, knowing that the density of the water is 1,000 kilogram per cubic meters, which can be converted to kilogram per liter. The 1,000 kilogram per cubic meters equivalent to 1 kilogram per liter, since the 1 liter equivalent to 10 to the power minus 3, 10 to the power minus 3 cubic meters. Now, the mechanical power increase of the fluid equals to the mechanical power output minus the mechanical power input. The mechanical power output from the pump, that's the mass flow rate times the fluid plus the actual kinetic, specific kinetic energy plus the potential energy. This is for the output, similarly for the input. Now, it tells us that to neglect the elevation differences, so GZ2 minus GZ1, that's 0. Besides, since the diameter of the duct of the pipes is the same, that means V1, V2 are also the same, so they will cancel. And with the assumption that alpha 1, alpha 2 are equal as well. So the mechanical power increase of the fluid reduces to this form, which after plugging in the values for the pressures, the density, and the mass flow rate, that results in 10 kilowatts. This represents the useful pump power. This represents the useful pump power. If you recall the equations we showed back in chapter 3. So this represents the useful pump power. So the efficiency of the pump, the mechanical efficiency of the pump now may be calculated. We have the useful pump power, we have the shaft pump power. So we calculate the efficiency, it will be 74.1%, 74.1%. Now, in order to find the mechanical power losses, that's simply what in the pump, that's simply the input to the pump, the input power to the pump, which is the shaft pump power, minus the output from the pump, which is the mechanical power increase of the fluid, which we refer to as the useful pump power. So that's 13.5 minus 10 gives us 3.5 kilowatts. This represents the mechanical power losses in the pump. This mechanical power losses in the pump results in an increase, in a rise in the temperature, which can be related according to this thermal energy balance equation. It equals to the mass flow rate times the change of the internal energies, the change in the internal energies. And as we learned back from chapter 5, the change in the internal energy for the incompressible substances as the water here equals, the liquid water here equals to the specific heat times the time and the temperature increase. Solving for delta T equals to 0.017 Celsius degrees. 0.017 Celsius degrees after plugging in the value for the specific heat of the water, which is found to be 4.18 kilojoule per kilogram Celsius. Okay. Okay, so that was for example 12.5. If we check example 12.6, in this example, in a hydroelectric power plant, 100 cubic meters per second of water flows from an elevation of 120 meters, as shown here, from this top water reservoir to a turbine where electric power is generated through this generator. The total irreversible head loss in the piping system from point 1, which represents the top surface, the surface of the top reservoir, and point 2, which represents the surface of the bottom reservoir, excluding the turbine unit, is determined to be 35 meters. So that represents the losses had in the piping system. If the overall efficiency of the turbine generator, is 80%. And we learned what do we mean by the overall turbine generator efficiency back in chapter 3. Estimate the electric power output. Estimate the electric power output. So, in order to know the electric power output, the electric power output, we need to know the what? We need to know the mechanical power the mechanical power decrease of the fluid. And then from the relation of the overall efficiency, we may calculate the electrical power output. So first of all, in order to find the mechanical power, the mechanical power decrease of the fluid, we need to apply the energy equation between points 1 and 2. So in order to do so, we need to find the mass flow rate. The mass flow rate is simply equals to the density times the volume flow rate. The volume flow rate is given in the piping system. So that's 10 to the power 5 kilogram per second. That's the mass flow rate in the piping system. Now, if we take point 2 as the reference level for the elevation, then the elevation of point 1 would be 120 meters. So apply the energy equation between points 1 and 2. Since these points 1 and 2 represent surfaces of the water reservoir, approximately they are stationary, their velocities are 0. Besides, their pressures are the atmospheric pressures. So as we can see, the pressure heads will cancel. Besides, the velocity heads also will cancel since the velocities are zeros, approximately zeros. There is no pump. There is no pump between points 1 and 2, so this pump head will also eliminate, it's 0. So the equation reduces to the form that the extracted turbine head equals to Z1 minus the head loss, We know Z1, we know head loss, so we calculate the extracted turbine head. So that equals to 85 meters. In order to get the extracted turbine power, which represents the mechanical power increase, the mechanical power decrease in the turbine, in the fluid through the turbine. So that equals to m dot times g times the extracted turbine head. We have everything, so we get it as 83,400 kilowatts. Now, from the relation of the overall efficiency of the turbine generator units, the electrical power equals to the overall efficiency times the extracted turbine power. And that results in 66,700 kilowatts, which converted to megawatts becomes 66.7 megawatts. Okay. This example here is for a fan. So a fan is to be selected to cool a computer case whose dimensions are 12 by 40 by 40 centimeters. Half of the volume in the case is expected to be filled with components and the other half to be airspace. A 5 centimeter diameter hole is available at the back of the case for the installation of the fan. That is to replace the air in the void spaces of the case once every second. So that gives us kind of useful information to be used later on. Small low power fan motor combined units are available in the market, and their efficiency is estimated to be 30%. That's the fan motor. So it's like the pump motor. Again, the fan, the compressor, we use them similarly to the pump. So it's to be their efficiency is 30%. Determine the wattage of the fan motor unit to be purchased. What's the electrical input power of this fan motor unit, and the pressure difference across the fan. Take the air density to be 1.2 kilogram per cubic meters. So that we want to know the pressure difference across the fan. Okay, so first the volume equals the void diffraction. It tells us that half to be airspace. half is for the filled by the components, while the other half is filled by the air. So the volume filled by the air equals to half of this space dimensions, 12 by 40 by 40. So half times the 12 by 40 by 40 results in 9,600 cubic centimeters. Therefore, the volume and mass flow, it tells us that this volume of air is replaced every 1 second, every 1 second. So that from this piece of information, we can calculate the volume flow rate as the volume divided by the time period, so which is the 1 second. So 9,600 divided by 1 second, that results in 9,600 cubic centimeters per second, which can be converted to cubic meter per second as 9.6 times 10 to the power minus 3 cubic meters per seconds. Cubic meter per seconds, knowing that every 1 cubic centimeters is equivalent to 10 to the power minus 6 cubic meters. Now for the mass flow rate, we simply multiply the volume flow rate by the density which is given. So that results in 0.0115 kilogram per second. That's the mass flow rate. The area here, the cross-sectional area of the opening in the case, the diameter is given as 5 centimeters. So we calculate the cross-sectional area, and from that we calculate the average velocity to be 4.9 meter per second. 4.9 meter per second. Here it's given information for the diameter hole, a 5 centimeter diameter hole. Okay, now if we draw the control volume around the fan such that, as we can see, P1 and 2, they're both open to the atmosphere, so they have atmospheric pressure. Apply this equation, we will calculate the fan power. There is no turbine between the points 1 and 2. The pressures again are equal to the atmospheric pressure. The flow is assumed to be, the inlet section is assumed very low velocity, so it's negligible. And V2 is the one that we calculate, is the velocity through the hole. So calculating for the useful fan power, which by bringing in here the losses in the fan, that gives us the useful fan power. Calculated, it equals to 0.152 watts. Now, with the knowledge of the overall efficiency of the fan motor, we can calculate the electrical input power to the motor, and we find it equals to 0.506 watts. 0.506 watts. So a fan motor rated at about half watt is adequate for this job. Similar to this. This is something very common that we see in the PCs. That's the kind of unit we are expecting to install. Now, the second requirement was to find the pressure difference across the fan. In order to find the pressure difference across the fan, we choose points 3 and 4, which represents the points upstream and downstream from the fan. And then we apply the energy equation. Again, the velocity will be the same since there is no change in the cross-sectional area. Besides, the elevation is the same, so the energy equation reduces. Z3, Z4 will cancel with each other. V3, V4 will cancel with each other. Then the energy equation reduces to this form. Again, the useful fan power equals to the mass flow rate times the pressure difference divided by the density. We have the useful fan power from the previous step. So we simplified the pressure difference across the fan to be 15.8 Pascal. 15.8 Pascal, that represents the pressure rise across the fan. Okay, thank you for listening. By this, we finished chapter 12, which talks about the Bernoulli equation and the energy equation as well for the steady flow. Okay, thank you for listening, and I hope if you guys have any questions, you may send me your questions through e-learning or by email or through our group. Thank you again for listening. See you soon, inshallah. Assalamu alaikum wa rahmatullahi wa barakatuh.